to do it.
Hello.
Hello.
Good morning, everybody. Um, Today we're going to start on chapter 20. Thank you, you guys, for the ones who have started on your concept maps and everything. Um, Chapter number 20 is going to take you in a little bit of a different direction. Um, just like thermochemistry, um, just like thermochemistry, electrochemistry is also one of my favorite chapters. Um, One of the things that I want you to do, make sure you go and look at the worksheet. I think I should have one. I'm checking now to see if I have one on electrolysis, voltaic cells, and I'm trying to see which other one. Corrosion and balancing redox equations. All of these is several of them, and I'm going to list them. You need to look at those worksheets that's under handouts, under modules. Those will be good worksheets to look at and to study for this last test that you guys are going to have for test 3. So make sure you take a look at that. So electrochemistry. Electrochemistry deals with basically the relationship between electricity and chemical reactions. Um, the reason why we want to deal with this is because we have to deal with spontaneous and non-spontaneous reactions and what happened with these different types of processes. Now, with that, um, one of the things that we have to look at and that we have not done that much of is assigning oxidation numbers. And one of the things is with oxidation numbers, you have to do certain things. Now, one of the things that you guys are going to need to do is pull out is your ionic charges chart. There's a reason for that. You have to assign oxidation numbers because now we finna work on balancing equation, but balancing half reaction. And I know you guys are going like, we know how to do that already. Well, this works a little bit different. And we'll talk more about this on Tuesday, but I want to get through this particular, through chapters 20 and 21 so that you guys can understand, because the math on this is a little bit different because you're going to be balancing chemical equations, but you're going to be balancing redox. So that's why I want you to read those sheets. And at the end, I'll tell you again which sheets you need to pull up. Now, when you're balancing these redox equations, you have to assign oxidation numbers. When you have pure elements, oxidation is 0. If you got a monatomic ion, that's the charge on that ion, meaning that it's just a single atom, like silver, gold, sodium. Of course, for fluorine, it's -1. Oxygen is tricky. It's usually -2, the charge that you see on your ionic charges chart. But if it's in a peroxide, oxygen is a -1. When you talk about hydrogen, it is +1. Now, unless it's a metal hydride, when you got a metal and a hydrogen after it, it's -1. Now, I am going to find some oxidation charts for you guys and post those for you so that you can understand how to balance those equations. Now, what happens? when you have to keep track of what loses electrons, what gains electrons, you have to assign what we call oxidation numbers. If the oxidation number increases for an element, the element is oxidized. If the oxidation number decreases for an element, the element is then being reduced. So let's take a look at that. Now, when we talked a little bit about oxidation and reduction in earlier last semester, but we didn't dwell on that too much. But now we're going to spend just a little bit of time on this. Now, species, when it's oxidized, it loses electrons. So what happens to zinc? It loses 2 electrons, forming the zinc 2+ ion. A species is reduced when it gains electrons. So hydrogen, H+ gain an electron, forming hydrogen gas, or the diatomic H2. And you have an oxidizing agent, which is the H+, causes something else to oxidize. A reducing agent, zinc, causes something else to be reduced. That is how you think of it. Oxidation and reduction, those reactions are written separately. That's why I'm saying they are called half reactions. So what you're going to do is we're going to use them to balance a redox reaction. So redox reaction are half reactions. And I know what some of you are thinking, man, I wish I could have did this first. And in some books, they do have this as one of the first things that they go over. Some books wait until they get to electrochemistry to do it later. So what they did here, they did the oxidation of 10. So they said S2+ aqueous yields SN4 plus 2 electrons. And that basically means 2 electrons, they lost 2 electrons. So they put the 4+ on here, and then the 2 electrons come off. Now, for the reduction, they got 2 Fe3+ plus 2E give you 2 Fe2+. And y'all know y'all guys are going like, what has happened there? Oops, I'm going too fast, hold on. Okay. Now, this is an example of how you would write these and how you would do the reactions. Now, I know y'all saying it should be 1+, but with iron, remember iron is a transitional metal. It just add differently. That's why I said I'm gonna give you guys, like I said, make sure you pull out your ion charges chart. That will help you a lot. And then I should have a sheet up there on redox reactions. And there are some redox reactions, half reactions that have already been solved. And I will post those for you as well so you can have those. Now, when you are balancing these redox equations, there's a half reaction method that you have to do. Now, the key to balancing these is understanding what is going on with water and hydrogen and oxygen. That is very important because they are used mostly to balance these types of things out. Now, what do? You make 2 half reactions. You got to know which one is oxidizing, which one is reduction. Then you balance the atoms. And you balance everything but the oxygen and the hydrogen. Then you come back and then you balance using water and H+. That's how you balance them. Then you got to add your electrons to balance the charges. And just like you do in regular balancing, you have to multiply by a common factor to make the electrons in the half reactions equal. Divide by a common factor or converting H plus to OH minus if it's basic, and then you just double check it. Now, what we're gonna do in the next few slides is actually go through this and see how this actually works. So let's talk about this. Now, this is the half reaction. So you got manganate, that's MnO4 minus plus C2O42. And what you get is Mn2 plus CO2. When you assign the oxidation numbers, you can show that the manganese is reduced. So the manganese go from +7, and you got to have your ions charges chart out, to a +2, and then the carbon is oxidized. It goes from +3 to a +4. Now, we're going to talk about that. You got to assign those oxidation numbers. Now, let's take a look at this. We're going to break this down. So with C2O4 going to CO2, to balance the carbon, we got to add a coefficient of 2, just like you do when you're balancing a chemical equation. Now the next thing, and everybody see that, right? C2O4 gives you 2 CO2. So we add the coefficient of 2 to balance that carbon. First thing you do, just like you do if you balance in a chemical equation. Now, the oxygen has to be balanced. To balance the charge, you got to add 2 electrons to the right side. So you got O42 minus is CO2. You got to add those 2 electrons to the right side. That's what you got to do in order to balance that. So everybody see that. Those electrons, so this part is balanced for now. One down there for. Excuse me about that. All right. So you guys see that it's balanced. Now let's go to the other side when we're talking about the manganese and the oxide. The manganese is balanced. We have to balance the oxygen. Now, we're balancing the oxygens. We got to add 4 waters to the other side. That's what we got to do. And I know you guys are going like, really? You just can't add oxygen. Oxygen has to be hooked on to something. And so in this case, you got to add water to it. So we add 4 waters. So that's what they did. 4 H2O. Don't freak out. I know y'all going like, oh my God, this is just crazy. There are rules to this. I'm going to find some rules. You guys can even Google rules if you want to solve these. But there are rules out there to doing the oxidation. Don't freak out. All right. When you do that, then you got to balance the other side. So what you got to do is, because you got those 4 oxygens on one side, you got to add 8 hydrogens, H pluses, to the other side. That's what you got to do. It's just like balancing a chemical equation, guys. I don't want you to freak out, because I know y'all going in your mind like, oh my God, this is crazy. No, it's just like balancing chemical equations. The only difference is you're dealing with electrons and ions. That's why I said you need your ion charges chart. That will help you a lot. So pull that out. You're going to need that. So make sure that you have that. All right. Now, that's what they did. They added the hydrogens to the other side. Like I said, just like balancing. So only thing that we're doing different than when we were balancing chemical equations, and like I said, I will go over more of these. I just want to get through the PowerPoint and you guys to read the chapter first, because it's a lot to digest. I just don't want to throw a whole lot of math at you. I just want you to sit and digest all of this, because we're not doing ice tables per se anymore. We're switching on. That's why I said Chem 2 is just a lot of math that is twist turvy and every which way. So that's what you do here. Now, you have to balance the charge. That's what's got to happen. So the charge over here, you got to be balanced. So to balance the charge, you got to add 5 electrons to the other side, because manganese is a +7 charge. So to balance the charge, you got to add the 5 electrons to the left-hand side. Because see, what has been thrown in the mix is, oh, now we got these charges, we got to put these electrons in there. So those electrons, you have to show those electrons are being moved around. And the reason why we're doing this is because we're dealing with electrochemistry, electrons. Remember when I say electrons drive the chemistry? This is what you are literally dealing with. So in this case, you gotta add those 5 electrons over there to that side to make sure that it is balanced. If you got questions, you're not sure about something, type it in the chat, because I got my chat window open. So all right, so with that, after you do that, okay, now what you're going to do is, now since you did them in half reaction, now we're going to combine everything together. So I know some people are saying, man, if we had did this in the first place, this would have been easier. Somewhat, but not necessarily. So what we're going to do is we're going to take all of them and we're going to set it all together. And what we're going to do to make the number of electrons equal on each side, we need to multiply the first reaction by 5 and the second reaction by 2 to give the least common multiple. So that's what you're doing. It's just like when you're balancing an equation. You just multiplying one side by the other side. So that's what they did. So they 5 equal 10. And so they did the bottom one, 10 equals 16. So that's what they did. So they multiplied the top equation by 5, the bottom equation by 2. And then what they do is they add all of it together. So 10 electrons plus 16 H plus, 2 MnO4 minus, plus 5 C2O4 2 minus, and this is what you get right there. So when you add those together, you get all of this right here. So you got 10 electrons on one side, 10 electrons on the other side. You got 16 H's here, 16 H's here, 2 Mn, 2 Mn. Let's see. They got 10 C, yep, 10 CO2, 10 C's, 10 C's right there. So you have to make sure, just like you balancing a chemical equation, that everything is balanced. All right. Then once you do that, you have to see what can you combine. The only thing that appears on both sides are the electrons. So the electrons are on both sides. So subtracting them, this is what we left with. So the electrons go away, and then we got 16H plus 2MnO4 plus 5C2O4, 2 minus. This is what you got. And then you just verify that the equation is balanced. And this is how you do half reactions. Make sure that what you do is you go back through this, you look at it. Like I said, I'm going to list the worksheets and I'm going to show you the ones off of Canvas that you need to look at so that you can go over this and study this for this chapter. Now, what happens if you got a basic solution? The same thing, you got to balance it as if it occurs in acid. Once the equation is balanced, what you do is you add OH minus to neutralize the H plus. If it's produced water on both sides, just like you subtracted out the electrons, you subtract out the water. It works the same way. Are you going to get a lot of those? A few, but not many. Now, one of the things that I really was looking forward to really doing was you guys making a voltaic cell in lab and doing electrochemistry. When you have these redox reactions, electrons are transferred and the energy is released. That energy can do the work if the electrons are flowed through an external device. And this is what you call a voltaic cell. Now, how the voltaic cell is set up, and like I said, the reason why I love this particular chapter is because one of the things that I studied in my research also was looking at lithium ion batteries. And one of the things that the basic thing that I had to learn first was really understanding the basis of a voltaic cell. And so here you have 1 mole of zinc sulfide solution on one side, and then you have copper sulfate solution, zinc sulfate, copper sulfate solution on the other side. So copper, you see that it's a blue solution, the zinc, and then you put the metal in it. Now, what we was gonna do was actually do U-shape, and we was gonna make a voltaic cell in the lab, and you guys was gonna run these and actually look at the voltage coming across there. And you guys will be seeing that in the lab that you're doing online. Now, just like batteries, you got oxidation that occurs at the anode, reduction occurs at the cathode. Now, electrons flow, the charges are balanced. So when electricity is on, the charges are balanced. So what they do is we add what we call a salt bridge. This is a U-shaped tube that contains a salt/agar solution to keep it balanced. So what we usually do is in that we put potassium nitrate in order to keep it balanced. So this is what you guys was going to do in the lab. You guys was going to actually set up something very similar to this and actually run that. And so that was one of the things that I really was looking forward to. Now, what happens with this? Because we're going to talk about batteries at the end. In the cell, the electron leave the anode and flow through the wire to the cathode. Cations are formed in an anode compartment. As the electrons reach the cathode, the cations in the solution are attracted now to the negative cathode. The cations gain electrons and are deposited as the metal on the cathode. That is what happens. So the metal, those ions come off and they actually transfer. Now, when looking at this, there are some other things that we have to talk about. Now, when we talk about voltaic cells and electrons, we have to talk about EMF, or we call this electromotive force. Now, think about water from a waterfall. Water flows spontaneously one way in a waterfall. Comparably, electron flows spontaneously one way in a redox reaction from high to low potential energy. That's basically what happens. Now, the potential difference between the anode and the cathode in the cell is called electromotive force. Now, it is also called the cell potential and is designated as E cell, E sub cell. So that's what you're going to see. It is measured in volts, and 1 volt is 1 joule per coulomb. For those of you who are in physics or going to take physics, you will see this again. Now, there are standard reduction potentials that are in water at 25 degrees C. That's why I said there are half reactions that are out there that have already been solved and already been done for you. That's why I said I will find a chart. This is also in your book, and there should be a chart in your book on this. So make sure you look at that. And like I said, I'm going to try to find one online and post it for you so that you can have that chart. Now, there are different electrodes that are out there. One of them is called a standard hydrogen electrode, or SHE, S-H-E. By definition, if you look at it, the reduction potential for hydrogen is 0 volts. But what they do is, this is how you look at it. You have 2H plus. If it's aqueous, if it's in a 1 molar solution, because that's standard, 1 molar solution is standard, plus 2 electrons will give you, back to your atomic, diatomic hydrogen, 1 ATM with gas. That's what will happen. And so that can happen in a lot of ways. And what you see here is SHE as a cathode, the hydrogen is reduced to H2, and then SHE as an anode, the H2 is oxidized to H2. Now, one thing about cell potential, we've been talking about intensive and extensive properties. Cell potential is based on potential energy per unit charge. It is an intensive property. So this is what you're looking at. E cell is equals to E cell ERED cathode minus ERED with the anode. So this is just standard cell potentials. So the standard ones that are out there. So let's take a look at this. Let me make sure. So for the anode in this cell, you got E is negative 0.76 volts. The cathode is plus 3-4 volts. So what you do is you have the anode minus the cathode, and I think that should be switched around, because I think on the other slide, yes, it's cathode minus anode. Let me make a quick correction on that, because they got anode minus cathode. It should be cathode minus anode. Let's see here. Let me share. Let me do this on the whiteboard. That should be E. And I'm going to put it cathode. They made a mistake on that. Minus E anode. So what should happen is, let me put some parentheses around that, is you should have had for the anode, give me just a second. The anode is plus 3, 4. So you had plus 0.34 for the anode. So it should have been 0. And that should be negative 0.76. And it should have been minus, and then I'm just going to put this in parentheses, plus 3, 4. And what the answer technically should be, I put 0.75, it's 0.76. Negative 0.76 plus. And what you should have there is a negative. It should be negative. So negative times a positive is a negative. So you have minus that, and so it should be a negative 1.10. Not positive, but negative. So I wanted you guys to see that because they made a mistake on there. And I wanted to catch that because it's cathode minus the anode. So make sure you make a note of that. Go back to that. Okay. So this should be negative 1.110 instead of positive because they just switched them around. So that should be negative instead of positive on that slide. So make a note on this slide that should be negative and those should be reversed. Now, one of the things that you have to pay attention to is oxidizing and reducing agent. The more positive the values are, the greater tendency for the reduction under standard condition. The stronger oxidizers have more positive reduction, and then the strongest reducers have the most negative reduction potentials. That's usually what happens in this case. Now, where do all of this come together from last chapter? Gibbs free energy and redox. Spontaneous redox reaction produces a positive cell potential or EMF. When you have this, you have E is reduction minus oxidation. This is true for all redox reactions. There are different types of redox reactions out there. Corrosion. Just looking at if you take a nail, anything that's metal, and you leave it outside and it rusts, that is a redox reaction. So all redox reactions go through that. Yes, that's a redox reaction. I know y'all going like, that is so weird. Corrosion is a redox reaction. Just standard because something is oxidizing, something is reducing. It is as simple as that. Now, how does Gibbs free energy fits into that? It's the measure of spontaneity. Positive EMF corresponds to a negative delta G. So how do they relate? This is the equation right here. Delta G is equal to a negative NFE. That's how they relate. Write that down, put that somewhere, you will see that. Now, F is the Faraday constant, and that's it right there, because that N stands for number of moles. So yeah, it all relates back to that. We're not going to get into all of that, but just know that equation. Like I said, some of this, you're going to see it more in depth in physics. So you getting exposed to this, and you should know about it, and you should know how to solve it. But you're going to go more in depth with this when you go into physics. Now, how is everything related? Here it goes. This is where everything comes back and relates. So I wish, and we'll talk more about this. So you got this delta G is equal to negative N, your Faraday constant, and E. Then you got G here that we just talked about, negative RT log K. And then you got E is equal to this, RT over NF log K. So this is how all of it relates. It all goes back to this. You guys know what G is, all of this stuff. All of this is related. Free energy, redox K. Everything that we've been talking about, even from last semester, goes back to this one diagram right here. This is how all of it relates. I know you guys are going to like, Dr. Jones, you have lost your mind. No, it really does. You're looking at gas, temperature, you're looking at Faraday constant, all of that plays a part. So this is how everything is related. Okay. So it breaks down to this one equation. So remember when we was talking about on Tuesday, delta G is delta G prime plus RT log of Q. So let's just say we solve for delta G. So what we do is here, we do negative NFE, because we substitute in, because that's what delta G stands for, is equal to NFE prime plus RT log of Q. When you do this, because K and Q are the same, they are solved the same way. And we talked about that back in chapter 15. All right, if you divide both sides by negative NF, you get what we call the Nernst equation. So the Nernst equation is this, is E minus E naught, E prime, parenthesis RT over N of F, natural log of Q. Or if you do it this way, you can get the log of Q. Now, if you use standard thermodynamic temperature and constants for R and F, this is your equation. Now, this is what I want you to do. I'm going to type it in chat. I'm going to type it on the whiteboard. Make sure you understand how these equations break down. You need to know how these equations break down, because like I said, this is all related. So you need to understand how this breaks down. So make sure you got all the equations written down for this right there. Write down the equations. Do an equation. I'm thinking that's what y'all gonna do as an extra assignment, is y'all need to submit these equations. Write them down. You need to have these equations. They are very, very important. So make sure you write them down. Now, with this, the Nernst equation, you can have what we call concentration cells. Now, what do you mean? Basically that a cell can be created with the same solution, the same substance at both electrodes. So what they showing here is you have nickel anode and a nickel cathode, and then they have a solution in there. And so what happens is you got your nickel in your solution that is 1 times 10 to the negative third, and then you got 1 molar. And then what happens is when you discharge it, basically the molarities are balanced out. And the Nernst equation implies that a cell could be created if it's the same substance. For such a cell, E cell will be 0, but the Q will not. Therefore, as long as the concentrations are 0, the concentrations are different, the E will not be 0. So what we're saying is you can have a 3 molar solution in one, you can have a 1 molar solution in the other. That's what they're saying here. You gotta have different solutions and look at concentration, and you can do that. And that's one of the things that I did wanted to do, is really look at how concentration affects a battery. And you just looking at, because think about it, you got batteries with different types of stuff in there. And so you want to look at concentration. Do we have to increase the concentration? Do we need to decrease the concentration? If I am a company that are looking to make batteries, I'm trying to use as less material as possible to charge the most money. And so I don't want that much waste, because, you know, we got to pay for waste to be disposed of. So that's what you're looking at as a company. And so this is important as far as knowing what concentrations to use. Oh, let me go back to that real quick. The reason why you see that right there, that is an electrical eel. And that's what an eel runs off. They look at the different concentration. So that's why they got a picture of an eel there. So that's what eels are, electric. And if you see those when you're out in the ocean or whatever, they can shock you and kill you. So you want to get away from those things. Now, why do we care about these cells? What's the application of all of this? We use them in batteries. We use batteries all the time. Batteries, portable, self-contained, electrochemical powered. 1 or more voltage cells. They can be primary cells. Primary cannot be recharged when dead. The reaction is complete. Secondary cells are rechargeable. So what you have in your cell phone are secondary cells when it comes to the battery. The battery in a cell phone is considered a secondary cell. A little Duracell battery, a AAA of a AA, that you just use one time and you dispose of, that you use it till it's dead, that is a primary cell. That's the difference. Now, prevention of corrosion, rust proofing. We live down here on the coast. If some of you guys have parents, friends, or somebody that you know that works at Austal, we're down here. Now, normally what people like to do with their boats is put a corrosion inhibitor on there. Why? Because salt water will eat up metal in a heartbeat. It will just dig into it and chew away at it. So when it comes to putting metal, especially different types of boats in water and everything, especially salt water, you want to put something on there to basically keep it from rusting and rotting out. So prevention of corrosion is one. Then you have electrolysis. And electrolysis is another thing that we can look at. So there are different types of batteries. You got lead acid batteries. So reactants of products as solids. The potential is independent of concentration. It's made with lead and sulfuric acid. They used to have those in cars. What you could do is, back in the day, even when I was growing up, I'm not that old, but when you seen that a battery was dying out, the only thing you could go and do, because it had liquid in there, you could actually go open the battery up and pour water in it, and it will keep it running a little bit longer. So that's what a lot of people did when they saw that the liquid in the battery was getting low, and you could actually see it, you could put water in there and extend the life of the battery a little bit until you could get a battery. That's what people did back in the day. Ask your parents about that. They will know about it. I'm serious. Alkaline batteries is the most common one, AA, AAA batteries. You got nickel cadmium and nickel metal hydride batteries. They're lightweight, they're rechargeable. The cadmium is toxic and heavy, so a lot of the hydrides are replacing them. Then you got your lithium ion batteries. They are rechargeable as well. They're light. They produce more voltage because lithium is more reactive. That's why I tell you guys all the time, our cell phones that we carry around, those things are dangerous. If the lithium gets into an air, if it's not controlled going into air and it just punctures and get into the air, yes, it can take out Weaver Hall. I mean, it is really that potent. And so that little cell phone that you carry around, yes, it is that bad. I mean, to the point that I know I had mentioned it before in class, that the batteries on the computers, that's why now they put the computers separate and they ask for you to basically put the batteries in something, put it in something separate. And when you're going on a plane, because they want to check the battery, because one of those batteries put a hole in a big 747 jet. And so these things can be really, really dangerous. Now, these are just some pictures of seeing the lead acid batteries and then the alkaline battery. What happens is it's a separator in there, a very thin one. The anode is usually zinc plus potassium hydroxide, and then the cathode is manganese oxide plus some graphite, and then there's a separator that is in there. So that's what's in your alkaline batteries. Your lithium ion battery, this is how this works. Now, you have what you call the anode and the cathode, and it can be made of different types of materials. You can use cobalt, you can use copper. They mostly use cobalt. That is what I worked on for my research when I was at Cornell, when I was working on lithium ion batteries. We was looking at that, and carbon. So those are the two things that we really work on. And you had the electrolyte. You can have a liquid electrolyte. You can have solid electrolytes in the batteries. It just depends. And then what you do is basically the lithium can flow from one electrode from the anode to the cathode, and vice versa. That's what was going on. So that's what would happen. Now, what happens when a battery actually die is, or you can short a battery out per se. The electrolyte, the separator, if the anode and the cathode meet, it just goes to zero. It just neutralizes. It's shorted out. So that's why the electrolyte is so important, so that it can help everything flow. So, like I said, this was one of the things I really worked on. We worked with different types of cobalt oxide particles. And that's what I looked at, and working on anode materials. So I did a lot of particular that work when it came to lithium ion batteries, because that's what most people do. How can we make the cathode better? How can we make the anode better? How can we make the electrolyte better? So those are different parts that you can really look at. Now, another thing you can look at is fuel cells, and that is when it's burned, the energy created can be converted to electrical energy. So this conversion is right now only at 40% efficient. The remainder is lost as heat. And a lot of people are looking at that now. And the conversion from chemical to electrical energy is supposed to be more efficient, and it's the basic for those fuel cells. They are not batteries. The source of energy has to be continuous. That's one of the things that, even though you look at it, that's one of the reasons they don't use it as much. Now, one of the things they have, and like I said, I don't know if I had told you guys, my uncle out in California has a Ford Flex, and his Ford Flex runs on hydrogen. Like I said, whenever I went out there a few years ago, oh my God, I just enjoyed going to the hydrogen gas station to fill it up. Now, hydrogen and oxygen forms water. The cells are twice as efficient as combustion. And so the cells use hydrogen gas as fuel and the oxygen for the air. So it's really neat to see that. My uncle is a former engineer, a retired engineer. So that's just one of the things that he liked to use. And so this is how it works. I mean, you can just run cars off of that. So in California, they do use hydrogen. They say it's a lot cleaner, and depending on, you know, population and everything. So you do have hydrogen fuel cells that are out there that people use in certain cars. Um, Corrosion. Corrosion is oxidation, and is commonly named is rusting. So this is iron oxide. Another area that I did research on is rust. And I know people's like, why in the world do you want to do research on rust? Well, come to find out that rust, even though it looks bad, it is still magnetic. One of the things that we was looking at with rust is treatment for people who have cancer. Looking at can we take rust and can we move certain cells if we inject it into the body, and can we take the cancer and actually move it out? Can we do something with that? Can it be a actual target for laser therapy? Injecting that in, what different types of things. So yes, rust can be used for that. Rust can be used to create electrical, because it's magnetic, electrical stuff in certain things as well. So just looking at iron oxide, iron 2 oxide, what can it be used for? Can we make it useful? And so that's what we was looking at. So what happens? Like I said, if you have a nail that is out there, you want to drop it on something, the iron is oxidized at the anode region of the metal. And so this is water drops all over that metal. So one side becomes an anode, the other side becomes a cathode. That is literally what happens with a drop of water on something that's rusting. And so what happens is the electrons from the iron migrate to the region that is acting as a cathode, and that's how the rust starts building up. So yes, is a redox reaction and a simple water drop, and that's what happens, and it acts as that. It's just that it's a slower redox reaction. It's just not something fast like you got a battery, you dial in your phone. It's just a slower reaction. That's all what it is. It's still a redox reaction. It's just a slow progressing one. Now, how do you prevent rust? So what you have to do is, there are several things. You have to really protect it. So one of the things you do is, because zinc is more easily oxidized, the metal is sacrificed to keep the iron from rusting. So what you do is you put a coating on there. And so that's one of the other things that I work with as well. In my research, I did a lot of things. And I know people go like, why did you do all this different types of stuff? And it's just because if something rusts, there's one thing. But what if you don't want it to rust? Like I said, boats, people got boats down here. Different types of stuff, even on your cars. I mean, even just, you know, sending my kids' stuff outside and it got different bolts on it, you don't want it to rust, you can put something on there to prevent it. And so you put something on there is do that. Now, what they do is with pipes, what they do is they take pipes, and if pipes have iron in it and if they bury it below ground, what can happen is the soil is an electrolyte. Yes, the soil can act as an electrolyte. And what they do is they put a magnesium anode in there that becomes sacrificial. They weld it together, and when they weld it together, that keeps the pipe from rusting. So that's what they've been doing, putting pipes up underground. Because what it is, some of the metal pipes, it doesn't matter. When it comes to water, water can be destructive. And so that's what they're doing. So either you can put a coating that has some zinc in it, you can put magnesium in there to sacrifice it. That's some of the things that they do to prevent corrosion. Electrolysis is another thing. You can have non-spontaneous reaction occurs if outside electricity is used to drive it. Now, when you use electrical energy to create chemical reaction, this is called electrolysis. And you do see that a lot when you're trying to speed up reactions, when we're trying to simulate different things. So you have electrolysis. And I mean, a lot of times you can do electrolysis in a petri dish. And that's one of the things I wanted you guys also to see, that you can do electrolysis simply in a petri dish. So right here, you got just molten salt, and you got an anode and a cathode there, and it just going across. So you can do it in a salt solution. You can do it in some type of nickel solution. You can do a nickel anode, and then your cathode can be steel. And some steels do have nickel in it. Most of it is iron and carbon, but you do have some in there. So you can do that as well. Now, let's see. Electrolysis and stoichiometry. The last thing that I'm going to cover for today is you have 1 coulomb is 1 ampere per second. Q is equal to IT. Current time, like I said, N is number of moles, Faraday constant. N is different than that for the Nernst equation when it comes to that. So just keep that in mind. We're going to talk more about that. What I want to do is steer you in a way of what do I need to do for this chapter? What do I need to start looking at? And I am going to share that with you. Give me just a second. Let me go to, I'm going to pull up this. All right, so I have pulled up your handouts. There are several handouts here. You got balancing redox equation, you got corrosion, you got electrolysis. Let me see what else is down here. Redox and voltaic cells. Those are all of the ones that, and then thermodynamics, that is from chapter number 19. So make sure you pull up all of those. So there are several ones that you need. Balancing redox, corrosion, electrolysis, and then these other ones that are up here, acid bases buffers, that was from the previous test. You can also look at those to study for your final. So all of these will be good review for study for your final. But for this chapter, for chapter 20, balancing redox equation, corrosion, electrolysis, redox, thermodynamics from chapter 19, and voltaic cells. These are all the ones that you need. If you make sure you print all of these out and start looking at these and start working on these. This is very important. So let me give you some hints on what you need to do for this chapter. And one thing that I'm going to do, let me do a new share. Let me go to the whiteboard. Okay. All right. All right. Do your concept map. Do the worksheets. Which ones did I name? Corrosion. Rotate Excel. Sorry, I'm going to switch windows so I know which one I told you guys. Electrolysis. What else? Balancing redox and redox control. Let me go back to my balancing redox and redox control. Work on that. The quizzes are already up. If you want to do the quizzes, that's fine. Go ahead. Make sure you read and understand this. Now, do your concept map, do your worksheet. So that's one. I'm going to say before one is read the chapter. Then do your concept maps. And then 3, work on those worksheets. Also, make sure that equation make sure you do an equation sheet. You're going to find this very helpful for you. So go ahead and start working on an equation sheet. This is just going to help you study. If you sit down, instead of copying one, make your own. If you sit down and make your own equation sheet, trust me, please trust me, you will learn this material. It works. It does. I'm telling you, it will work. Make your own equation sheet. So equation sheet, I'm gonna go back and be like, make your own equation sheet. This will, and you can do this by hand, because if you write it out, you will understand it much better. If you want to do it on the computer, that's fine. Make it by hand first. Write them down. If you write them down, you will remember it better. So make your own equation sheet. This will help you study. So do that. Those are the things that I want you to do. Ooh. Let me put that capitalized, all of those. Make your own equation sheet. It will help you study. I guarantee it, you guys. I've done it. Several of my colleagues that teach science classes that major in math, physics, chemistry, biochem, when you make your own study guides and your own, I like to call them cheat sheets, but when you make your own equation sheets, it helps you study a lot better. So to get you prepared, this is one of the things. that you need to do. Make your own study thing. If you have any questions, please reach out to me. Email, call. What I need to do and what I am going to do really quickly when I get off with you, because I have another class at 9:30. I will look for some half reaction sheets on, I'm going to Google them online and see can I find some, and I will post them for you. So I will look for half reaction sheets and try to post those for you, so that you can have some experience at doing this. You guys have a good one. Stay safe. Like I said, if you need me, email me, send me a message on Canvas. Just reach out to me if you need anything. I got to go. I will talk to you guys on Tuesday. All right. Have a good one.